So welcome to the very last session of this wonderful conference. It's my great pleasure to introduce Chenchang Zhu and her talk, Higher Differential Geometry and Symplectic Structure. So
Thank you for the organizer. At the beginning, I thought such a density of talk. I was really afraid, but maybe after that, I think there is advantages. Thank you. And before my talk, well, it's the last section, so maybe people are tired and some relaxation. So let me first advertise something. So oops, it doesn't work. It works in my computer, it doesn't work here. When you click on that, maybe someone can click on that. When you click on that, it's Alan's 80th birthday in Paris, and at this time, June 19 to 23rd. And the thing is that there's still financial support available. So contact the organizer of the conference. And the next thing is there is a Dorothea Schlüter female postdoc program at the home of Gauss and Riemann. Noeta Hilbert, namely in Göttingen. The deadline is April 15th. If it is not for you this year, it will be there every year or every 2 years. So is it something to keep in mind? Don't worry. And I finished it already. And when Ivan have the slide, you can click on that.
Exactly. The slides are gonna be shared. So
yeah, exactly. And then there many derived phenomena appear in this talk, and the derived geometry is a very nice way to resolve singularities, like when you pull back a zero section and there is not a good point, direct geometry is a wonderful way to resolve this sort of singularity. And many years before that, there is also higher geometry. That's a way to more like a way to resolve such sort of singularity when your group acts on something and that action is not proper, not free, and then you can use higher stuff to resolve that sort of singularity. But more than that, I think then there are also other sources why these higher things appear. For example, in TQFT, if you understand TQFT as a function from the categorical Buddhism to that of vector spaces, when you raise the dimension, for example, in our universe 3+1, you would just need higher function and higher categories. That's like what I observed, like a huge energy that drive us into this. And then of course there's Lurie's and Towen's foundational work in algebraic geometry of those Lurie's higher topology theory, and also in differential geometry, the Poisson community and the community of Bayes and the Strauss-Teichner program. They over there, they also like plenty of high structure shows up. And in this talk, I'm going to present you a model for higher differential geometry, and namely higher Lie group points. And they should be understood as the chart for higher differential stacks. And then I put all these Lie group points together, and I tell you what kind of word these higher Lie group points stay. It stay in is an incomplete CFO category fiber object, and it's that will generate a very nice very simple higher category for you. So they live in a nice word. And the last thing, I will put some symplectic structure on these higher structures. Okay. Category of favorable object. There is a slide, but thank you. You can also understand as like a coordinate for higher categories, which you can generate. Okay, so let's start a little bit like introduction, and then let's before this higher group, right? Maybe I tell you like there are many years ago, there's maybe we first talk about higher group. So before higher group, let's first talk about group. Group is a set with a multiplication, identity, and inverse, right? And they satisfy certain axioms. And then to get a higher group, there's a very convenient, very philosophical categorification. Very convenient way to do it. You by categorification, and you replace a set by a category. Then your multiplication, which was a function, will become a functor, right? So like now everything, this guy is a functor now. And the same thing for the other two structure, you've got like a functor. Let's focus on multiplication. And then multiplication, before you need to satisfy associativity, but as soon as you have a functor, you see, you will have a diagram between categories. And you do have room to play, namely you can say this diagram does not strictly commute. It commutes up to a natural transformation. And this is the associator. And over here, you could have also other like two morphisms. And then you go one step further. This associator will satisfy pentagon condition. That's the before we have these guys, and the associator itself is a constraint, right? And over here, associator is a data, and then you have on the next level you have a pentagon condition, which is a constraint. And here you can imagine like these guys need to play together. You have maybe several diagrams to check, and people sort it out on this level, and you can write it down in 2 pages. And this is a very nice way to very philosophical to understand higher structure, higher groups, for example. But the cost is that you need to verify a lot of diagram, right? You see like here 3, and it seems like the complexity goes exponentially higher, which in the end is not the case. But you have the potential to go very high, but which is not a bad thing. It just shows how rich it is. So the next attempt to understand this is via something. It's via higher group height, via simplicial method. If you do via simplicial method, you found like it's a polynomial cost. So let me remind. A simplicial, let's just start with the set. Simplicial set is a tower of set. So here you should the typical example you keep in mind, you take a topological space X, you take the 0 simplices, 1 simplices, and 2 simplices, and so on. And you have 2 face maps, 3 face maps. And over here, you have 1 degeneracy, here 2 degeneracy, you have all these set of maps. So that's a simplicial set. And to understand the simplicials, to make the simplicial set further a higher groupoid, you need a Kahn condition, where I draw the picture over here. So Kahn condition says, so MJ says from this set of M simplices to the set of horns, J horns. And what is horn? That here I just give some pictures. I hope you can. That's good enough to understand. It really looks like horn. Namely, take the M simplices, you remove the inner and the J space, and you put all these things together, and the set of such things is this guy. And of course, there's a projection from M simplices to horns, and you are this Kahn condition that this projection is surjective. Namely, whenever I have a horn, I can feel it with a M simplex. Filling might not be unique, but I can feel it. And then, of course, it sounds like a good thing to have the unique filling, which is a strict Kahn condition. Over here, I require it to be a isomorphism instead of just a surjective map. So these are Kahn condition. And what does Kahn condition have to do with the group structure? You see, like here I have a horn and I fill it. It actually shows that I have a multiplication, right? And if my horn goes like this, even demonstrate some sort of inverse. And of course, the other guy also. It actually is redundant as one day as well remarked, right? And if the base is a point. And then, maybe I even prepare more. Like, what happens if you have two fillings? I said like a Kahn condition only says that you have filling, right? If you have two fillings, a straight one and a curly one at the back, is you have two sort of multiplication. And what happens if you have two sort of multiplication? You can over here have a degenerate edge, because for simplicial set I have degeneracy. Then I have a straight triangle, a curly triangle, and a degenerate triangle like this. They form a three-dimensional horn. And my Kahn 3-1 facing 1, this condition tells me I can fill this tetrahedra, and I've got like a face here, right? The curly face here. That just tell me two sort of multiplication, they're homotopic to each other. But the point is that the homotopy might not be unique. But if you have two different homotopy, the higher Kahn condition tell you that you can feel this two homotopy too. But then the filling homotopy might not be unique. And you go further and further until one day you hit the strict Kahn condition. So that's my first definition. A simplicial set X dot is a n groupoid and can be 1 until infinity if it satisfies Kahn condition for Nj, for all Nj, and a strict Kahn condition when your m is bigger or equal to n plus 1. So after a certain point, you have to say my the possibility of homotopy like disappear. There's just one possibility. Okay, so then there's differential, like if you do in this way, the categorification way, and this higher way when n equal to 2, because people didn't do further anyway for the categorification method. These two concepts are the same. Two methods give you the same thing. Same concept. So now, since we didn't really go and categorification higher and higher, therefore we can use this one as the working definition, and moreover, this one also works for Lie group if you replace this. So you put some subjective submersion and simplicial set replace to simplicial method. So with this method, you can very, very easily work with a category with topology inside. Yeah.
Having a weak two group. What else do you need to have a strict one? Do you know?
What do you need to have a strict one?
To strictify, to know that it's strict, or is an F of a strict group? Or
you need, yeah, right over there. You need this, where you need all this two morphism to be identity, right?
I mean, if you have a weak to group,
right?
Can you say when is it coming from?
Right.
From
you first use this one to go from your concatenation to one of those models and verify that guy's identity. Yeah, you can calculate, and then the next thing, like next thing is to make you very relaxed. So it's the theorem to be by Laurent Dange. It will be in his thesis. He actually showed that you actually don't need conditions. It's actually any simplicial manifold x dot, they always satisfy condition locally near x0. So which means that given any simplicial manifold, you fix a number n, then there is a neighborhood of x0 that the condition will be satisfied over there until n. And then when n goes higher and higher, your neighborhood goes smaller and smaller, right? So that's very nice because it says that like every simplicial manifold is actually some sort of local group point, local higher group point. And then well that and also that shows like you can differentiate all simplicial manifold, right? Already, like before, when we do differentiation, we didn't use concatenation like dramatically. That already make us to doubt this, right? And you can differentiate all simplicial manifold to its tangent complex, which is x0, kernel P11, P2, kernel P22, and so on. So this P is this Hom projection. And then here we sort of so that's the first step is and now I'll give like two sort of, maybe the next you also have another way to interpret your higher object, namely you use some sort of GG manifold. Namely it's that's more like an infinitesimal method over there. which is well, it's more like a z z greater or equal to in the other direction will be the derived direction. And these manifolds, they should play an infinitesimal object for this higher Lie group, right? And I didn't update my slide. So let me go here. Yeah, exactly. So the interplay between them is differentiation and negotiation, integration, and there works previous to this. You can integrate nilpotent L-infinity algebra that's worked by Ezra and L-infinity algebra to L-infinity groups, and then if you make the base bigger, you can also have like a higher Lie group, right? And then there's the integration, local integration by Schauer and Siran, and then the other direction is is happening now and work in progress. Very I hope very much to the end. Then maybe I mentioned even another simplification for this higher object and then move on. So for like calculational purpose in sigma model, like in topological orders, we need even much more concrete things than just complexes. And over there we use this notion, namely we begin with a group G and billion group. So some sort of chain complex of a billion group, except for the first one is not a billion. And then G has an action on each one. Then I remember some cocycles. This is like associator. After this associator, I can form a two group. Then A4 will be a two cocycle of this two group with value in tau3, pi3, another billion group, and so on. You go then when you have an N group, then you can certainly let's call these things, I think we call it N tower. I call it N tower plus. Every time you have a N group, no, the other one. Every time you have a N tower, you can build up a N group. So these data is much more easy to calculate in your sigma model, right? But then whether a N group can go eventually is the same as N tower, that's conjecture. It's obvious when N equal to 2 by basis result, but when N bigger or equal to 3, one need to prove it. Okay, so that's enough for these higher objects. Let's have a look of what kind of word they form. We put them together. Oh yeah, so we put all of them together. I hope they form a nice category, right? And so at first, Chris and I were sort of wish they can form a category of five-bound objects, and which has all these axioms 1 until 7. Probably don't have to. I actually first saw this in Ezra's talk, and so you put all these higher Lie group highly groupoids together, are they CFO, right? And well, it turns out that it just it's like we cannot all the like if we verify 4, 5 is not there, we verify 6, 4 is not there, like we cannot always have it. And then in the end, we created something here. So after a little bit change, which we call it incomplete, namely you need to add one little condition, it does form a incomplete category fibrin object. But you see, like to have CFO, the point is that as I just said, like you wish your CFO to generate a nice higher category for you, because they are like coordinates for higher categories. But if I destroy this structure a little bit, does this property still hold or not, right? That's that is very important to verify this key step, where the Brown's lemma still hold for this ICFO. And it turns out that is the case. And therefore, like you can still form the simplicial localization, and that will be your higher cat. This one will be a higher category, and the home space of your the home space is very nice. It's just some span of to say this more in words, you just say that in your higher category, the word of higherly groupoids, it's enough to remember morphisms like this. One lag is either weak equivalence or hypercover. That's your one morphism, and 2 morphisms are either weak equivalence or hypercover, and then 2 morphisms are like this. So you don't need to remember more. That's enough. 1 morphism like this, 2 morphism like that, and that's all. And okay, so now I'm going to switch to the next part, namely, I want to put some simplicial not Poisson, symplectic structure in this word. Symplectic structure in this word. And that was how do symplectic structure enter this ICFO, or enter my word of these high stacks. So that was actually like when I graduated, I went to Zurich, ETH, and then Dima was asking me, "Hey, Chenchang, you're doing all these things. Me as a symplectic geometer, what is the symplectic structure on these?" And I said, like, my first guess will be, like, I've got all these things. I must have a symplectic form over here. And so that's the quotient, or 2 form, or pre-symplectic form over here. So that quotient will inherit a symplectic form. But then Dimas, then how about the kernel of this guy, right? Is it constant or not? Because the even if it is a Lie groupoid, you could have non-constant like isotropies. Then I didn't know. And Alan said, well, at least at this point, like for a tau stacks, it's clear, isn't it? Like then. That's an easy way to get around. But then Alan said, but Chenchang, like what about my symplectic groupoid? Then the symplectic groupoid is something that you have a omega not on x0 but on x1, right? So for many years I was carrying this question hard and I didn't know they should have some like reasonable way to host them, right? And then until I saw this concept of shifted symplectic structure, and I think that's a way to answer these questions. So to introduce shifted symplectic structure, let's first look at the Durham complex for a, let's say, either complex, a kind complex, or a simplicial manifold. So that one will have Durham complex on each level, right? And they talk with each other with this little delta. Delta is the alternating sum of these phase maps. And then to make our model more calculable, I take the normal complex. They have the same normal complex, and the Durham, they calculate the same homology anyway, right? And it's just a technical condition. And then, then let's say, then a unshifted K form omega on a Lie and groupoid X dot. All these N and K and M, they can be like 3 different numbers, is a omega equal to like omega K, which is a K form, live on X M, then a K minus 1 form, sorry, K plus 1 form until the K plus M form on M. So they live somehow, for example, shifted 2 form lives here in diagonal, but does not go all the way up. And then we brought, why start from, I give the responsibility to Ezra. I followed his development notes. Maybe this K is not very, one could have K minus 1. Tony says so. In the case of stack, and we have a total differential, right? And so it's easy to define what is pre-symplectic because it's easy to define what is closed. And but it's not very easy to define what is non-degenerate. So to define non-degenerate one, what was the non-degeneracy before? We take, if not a group, it's just a space, right? It will introduce the symplectic form will give me a map from tangent to cotangent, and I want this guy to be an isomorphism, then it's non-degenerate. And if I have a groupoid, this guy is another tangent groupoid, right? That's fine. And if I have a groupoid, I can also talk about cotangent groupoid, which is already like a little bit weird. A star, A is the algebraic, and you see it's not obvious. And I think it's work by Matthias, or I might remember wrong. The sky is non-degenerate in the case of one groupoid, if and only this is Morita equivalence. Sounds reasonable, right? Non-degeneracy means isomorphism, and higher isomorphism are Morita equivalence. But the problem, okay, let's go higher. The problem is that we don't know about cotangent bundle that I got explicitly. I think we just it will be Stefano Ronch's thesis to totally figure this out. But when we figure out like in the 2 case recently, and we hope that will provide us a way to reinterpret this non-degeneracy. But Ezra has a much quicker way, and we borrowed his formula in the notes. So the idea over here is that, okay, it's very hard to talk about tangent and cotangent groupoids, but for tangent complex and cotangent complex, once I have, I enter the word of complex of vector bundles, it's very easy to define what is dual. If I go there, and if I can do some infinitesimal multiplicative form, IM form, and then if I can differentiate this via some sort of Van Est, then this guy should go from tangent complex to cotangent complex, and I just have to ask this one to be a quasi-isomorphism. And so we borrow the formula from Ezra's notes and lecture notes. And I think this, when n equal to 1, it coincides with the first term of this IM form. So I would imagine that even in the higher case, if one day we figure out what is Van Est for higher groupoids, this one will be the first term of the IM form. And but then one can verify that this is easy to verify. And the second one is a little bit harder. You can verify these properties of this IM form that will make sure that this IM form define a complex morphism of complex. And once it's a morphism complex, you can define exactly like before. So you can define the non-degeneracy by saying omega is non-degenerate if and only the infinitesimally it is a quasi-isomorphism. And then you can define finally you can define M-shifted symplectic form on Lie groupoid, which is going to be closed M-shifted 2 form. Okay. So now we finally had a definition for these higher and shifted symplectic forms. Now we have a look of some examples. So if this is M, this is M. So 0 shifted form on 0 groupoid, namely a manifold, is just a symplectic manifold. 0 shifted on only 1 groupoid, that's the symplectic stack that Dima was asking me. And in that case, the shifted version, shifted formula does force you to have constant kernel of the omega, namely force you to have to make this x1, x1, x0 with constant rank, constant. So that can read from the non-degeneracy, and then when you have a one shifted groupoid, right? So one shift, one stack. I wrote in blue means it's the infinitesimal part. In yellow, no, in black, it's the global part. It's going to be this quasi-symplectic groupoid, right? And but then something can go wrong when your direct manifold is not integrable. Here's one shift still, but here is going to be a two groupoid. And then when you have two shifted, one, and you have this BG I will talk about, and two shifted two, will be this Courant algebra, which is still infinitesimal, but at least now we know what is the concept to integrate this. It will be a two shifted lead two groupoid. That's the concept to integrate it. And okay, so let's talk about BG a bit more. Oops. So that's the model for BG. So we have these two models. So the first one is a nerve of G, and that's certainly a model for BG, right? And the other one is a two groupoid. Actually, this is a strict two groupoid. And here is the path based at identity. Here is the based loop. You see, based loop acts on based this path, and the quotient is exactly G. So these guys are Morita equivalent. That's fine. And on this one, over here is the Cartan 3 form, 1/2 of Cartan 3 form. And over here is 1/2 of we call it Weinstein Brzezinski form because it is simply it already happened appear in Brzezinski's book and also in Alan's article in the dedicated to fluid. So it's this one. These theta L, theta R, they are Morita 1 forms, left or right translated. They live on G times G with a 2 form. And over here, this omega is the Siegel's 2 form, which is a symplectic form when you restrict to base loop space, right? And from omega G, from path G to G, you have an evaluation map, which is the end point of your path of the other end. And from loop to G times G, you also have another sort of evaluation. So you imagine your loop as some sort of triangle, then you evaluate at the other 2 points. And it turns out this is one of those hypercovers I construct before in this ICFO, in this word. And the whole thing form a symplectic Morita equivalence because you have a zigzag of hypercovers. Identity is certainly hypercover. This is a hypercover, zigzag hypercover, and a condition on the forms. And the condition on the form is this. So a symplectic Morita equivalence you have is a zigzag, so that the difference of these two forms is not 0. If it's 0, it says this is Z. If it's 0, it says that going to X and Y is a Lagrangian, right? But it's not exact 0, but it's 0 up to homotopy, which sounds good too in this context. So it's a n minus. So you give yourself an n minus 1 shifted 1 form, and the zigzag satisfy this condition. That's the symplectic Morita equivalence And when n equal to 1, that coincide with Hing's Hamiltonian bimodule, which is his way to define symplectic Morita equivalence before. So and then the final theorem is that we verified this as this zigzag with with Siegel's form putting on this level. We tried many forms, but in the end, this form works. Like how we try many things in the middle and many forms, and after 2 months, after Christmas, this one worked. We almost gave up, and then we also found out there's 1/2. Before we just thought they're the same. Yeah.
I mean, stopped at column 2. How does it continue?
Oh, it's code.
So that we know what the sufficient manifolds are.
Yeah. Thank you. So actually, yes. Actually, there's a way called co-skeleton construction. We actually all like for 2 group weights, the first 3 level are the only useful information. All the other things can be co-generated, co-skeleton generate. Yeah, and
So also all 3 of these symplectic manifolds are.
I'm totally wrong. I'm sorry. You need to stop at here.
Yeah. Well,
Yes.
that's why
Yeah. And I constructed there, but I didn't write over here. Yes. So for the first one, you don't, right? Because of 1 group. Yeah, exactly. G equals G equals G, and the other one is maybe I just 0. Maybe 0, 1, 2, 3, and you use 3 loops to glue them together, right? And we wrote down explicitly the space maps and degeneracies in the article. Yeah, thank you. And then afterwards, you can just code using co-skeleton to generate it. Thank you very much. Oh. Yeah, it's
Thank you very much. Any questions?
How about negative shifted forms?
Yes, thank you. So you see, like with these higher structures, you can, if you look at it a little bit, you can only have positive shift because your tangent bundle, your tangent complex live here, like here m, here -1, and so on, and the cotangent complex will live. This guy has degree -m. I mean, maybe I don't use m. M and yeah, it's the same m, and this guy has degree minus. So if you want to match these 2 so that they can talk to each other, you need to shift m. So this guy lived here originally, like so, right? So you here's a tangent complex. You take the dual. That guy lives there originally. Then you, that's really bad. So I mean, so the other one, well, then you shift m over here. Here will be 0. Here will be 1. So you definitely then you need to shift this number m, which is a positive integer because your tangent complex start at a positive integer for these higher objects. And when you want to have, and the -1 shift or -2 shift, they appear when you have derived structure, where your tangent complex goes the other way. Thank you.
Thank you for the nice talk. I want to ask you about the Morita equivalence that you were mentioning before. I think it's the previous slides. I don't know if you can go.
Right. Yeah.
This definition, yeah. Even in the very particular case where you have m equals n equals 1.
Yeah.
You know, can you tell how this relates with the principal by bundle approach?
Yeah. So right. So
at least when X and Y are strict, no, let's say.
that's not actually okay. Like so here you've got that. So we use this zigzag because when you go higher, this principal bundle will become very, like you have many, and it's hard to talk about, but this guy will still be the same. What do you do? Like you first, because this is a strict map, right? Then you first associate this guy a bimodule, a bimodule here. And you associate yourself a bimodule here with respect to this map. You have two bimodules. They are Morita bimodules, and you compose them. And that will give you the bimodule you want. Yeah. And there's a way to absorb the forms too. It's in the article, right?
So there's a question in the chat. Sorry.
Yeah.
So Ying D. Kim asks, does the shifted symplectic structure on Lie algebroid uniquely leads to a shifted symplectic structure on the Lie groupoid?
Yes. That's the integration problem with the symplectic form inside, right? For Lie algebroid, one thing is solved. So a shifted symplectic structure on Lie algebroid is a direct structure, and it does slip to a one shifted symplectic structure only Lie 1 groupoid or Lie 2 groupoid, depends on whether your direct structure is integrable or not. So that was like this thing, and it's not new, right? But definitely it's a new language to talk about this, right? But already 2, we don't know. Yes, right? We don't know completely how to integrate this 2 thing yet. Yeah.
Thank you very much. I'm ashamed to say I don't have a question. I just have a little comment. I want to put in a plug for Schulman's thesis at Berkeley in 1968, because what you called closed K-forms are already in his thesis under the name the Kth filtration in the Hodge structure. So he has that, and his theorem was that the characteristic classes of degree K lift to closed K-forms in this sense on BG. And so in particular, what you called the Brzezinski-Weinstein 2 form is already in his thesis.
Exactly.
Yeah.
Thank you so much.
I just wanted to point that out in 1968. So the thesis isn't published, but I put it online. I don't know. I hope it's not covered by copyright.
I didn't find that online
Oh,
thing.
we'll
You
double
know what?
check.
I asked
Okay.
my student to
Okay.
dig it out.
It's in the folder. Okay, but
And he
okay,
didn't
but I
find
have
that all.
okay, but I'll fix that. But one
Thank you
last
so much.
comment is that it was then, if you like, rediscovered in the context of the WZWN model, which is somehow what this differential form on BG is underlying, and by Polyakov and Wigman. So in physics, it's often, this two form is often known as the Polyakov-Wigman formula.
I see. Thank you. So thanks, Ezra, for the comment. Like the first time he made this remark, I went back home. There is a master student, and he wants to write a thesis. I dig out all I can find out without that PDF file. Maybe the Google is not strong enough in getting. Anyway, but he did verify, like Schumann has a method to do it, very nice method. And then it was actually based on, well, he's a French. You found out actually that one is actually based on a monsieur. Someone's article also in the 50s and so on. Like he did all this out, and he in the French article also described this. It's some sort of Czech Durand method, and then he finished his thesis, and yeah. So as well, I did the homework. Yeah.
One last question.
In your last example, you had some infinite dimensional thing that was Morita equivalent to a finite dimensional model.
Right.
Is that always the case that up to a Morita equivalence or an hypercover, if you start with a DG, if the underlying DG manifold is finite dimensional or finite rank, then you always get a model which is finite dimensional?
I should be able to do that. I think. So that's the integration problem, right? Can I finite dimensionally integrate a finite dimensional Lie2 algebraic or Lie3 algebraic, right? But
I understand, but even if you start with a n-groupoid that has an underlying DG manifold,
yeah,
which is finite dimensional. So so you already know that integrates to something.
Yeah.
Can you find a finite dimensional model then? Can you show that up to an hypercover or a Morita equivalence? You have a finite dimensional model.
I see. So you're saying that I have a shifted symplectic form somewhere in certain model, and I know there is there is a finite dimensional Morita equivalence, right? And in that case, whether I can make it symplectic, that probably depends. Maybe I need to modify the definition of the shift. Yeah. So that there are certain examples appearing, but not finite. Not even finite or infinite. I just have some say two groupoids. It carries something. It's not here is a two groupoid with a two shifted symplectic say, which start at omega-2, and here is a Morita equivalent copy. But when I transform here to here, it all of a sudden start from omega-1. I do not know you see, by current definition, this is not too shifted, right? I do not know yet whether I should change the definition or I don't call this guy the good one. So yeah, so even without infinite or finiteness.
Sorry. Thank you very much for the discussion. I have to stop it because we need to start the next topic.
Thank you.